Section 6.6, Exponential and Logarithmic Equations. An exponential equation is an equation with an exponential expression. In this section, we're going to take a look at two different methods on how to solve exponential equations. The first method will utilize the one-to-one property of exponential functions. The one-to-one property of exponential function states, if b to the m equals b to the n, then m equals n. Meaning if I have two equal expressions of the same base, their exponents must be equal. If we start off by taking a look at the equation 9x squared minus 7 equals 27 to the x, notice how both sides of the equation are not the same base to some power. The first thing we're going to try to do is rewrite both exponential expressions on both sides of the equations, so that way they do have the same base. If we look at 9 and 27, they're both powers of 3. 9 we know is 3 squared, 27 is 3 cubed. Now we can use the power to a power rule, which states if I have a power raised to another power, I can multiply the two exponents. 2 times x squared minus 7 is 2x squared minus 14. 3 times x is just 3x. Now I've successfully rewritten both sides of my equation, so that way they're in the form of 3 to some power. Now I can go to step 2 and use the one-to-one property. The one-to-one property is going to tell me that the 2x squared minus 14 and the 3x must be equal. Now that I've used the one-to-one property, I can see that I'm left now with a quadratic equation. Now I just have to solve that resulting equation. Since our equation is quadratic, I can subtract over the 3x to make one side 0. Now you can either factor or use quadratic formula, but 2x squared minus 3x minus 14 does factor to 2x minus 7 times x plus 2. And if we set each factor equal to 0 and solve using the zero factor principle, we get 7 halves and negative 2. Next, we're going to solve 4 times 1 over 36 to the x plus 2 equals 866. Notice that in this equation, we only have one exponential expression. We're going to start by isolating that exponential expression. So we have 1 over 36 to the x equals 216. Even though 216 is a constant value, we will still want to try to rewrite 216 so it has the same base as 1 over 36 to the x. Focusing on the 1 over 36 to the x, since 36 is smaller than 216, it'll be easier for us to rewrite. We know that 6 squared is 36. So 6 to the negative second would be 1 over 36. Using our power to a power rule, 6 to the negative 2 to the x is 6 to the negative 2x. Now that I can rewrite my left-hand side as a power of 6, let's see if we can do the same thing for the right-hand side. Can I rewrite 2 to the 16 as a power of 6? Yes. 2 to the 16 is 6 cubed. So I've rewritten both sides of my equation as powers of 6. Now I can use the one-to-one property and set the exponents equal to each other. Now I can solve the resulting linear equation, divide both sides by negative 2, and I get x equals negative 3 halves. Notice how I did not check the solutions. Remember, anytime you solve an equation, it is best practice to check. But here with exponential equations, as long as our exponents are expressions that have an all real domain, then we can get away with not checking, since our exponential functions also have a domain of all real numbers. What do we do if we can't rewrite both sides of our equation so that way our bases are the same? If we take a look at example 2 and try to solve 6e to the x minus 8 equals 16, this is very similar to the last problem, where the first thing we would want to do is isolate that e to the x. And we have e to the x equals 9 halves. But how do we rewrite 9 halves as a power of e to try to use the one-to-one property? In these kind of scenarios where we can't think of how to rewrite both sides of the equation so that way they have the same base, we want to start using logarithmic functions to help us so that way we can use their properties. So for this strategy, when we can't use the one-to-one property, we want to start off by writing the equations into the following form: a b to the u equals c d to the v, where a, b, and c are just constant numbers, u and v are some expression. I've already done step 1 by isolating the e to the x. However, I could have stopped at isolating 6e to the x. But if you can isolate the exponential expression, it is still worth doing. It'll save you more time. From there, we can apply a logarithm to both sides of the equation. Now, it's up to you which logarithm you want to use. You can use a logarithm of any base. However, oftentimes we are going to want to punch our solution into a calculator to get an approximation. So I highly recommend using either the common log or the natural log, so that way you can go straight to your calculator if they want an approximation. Now, here we are working with base e. So out of the two logs, the best one to apply here would be the natural log. That's because the natural log of e to the x is just x. As for the right-hand side, natural log of 9 halves is irrational, so I'll keep it as natural log of 9 halves. But if you do need to approximate it, you can punch it into your calculator. Next, we're going to solve 4 raised to the 3x plus 2 equals 3 to the 5x plus 4. I won't be able to write 4 and 3, so that way they're the same number to some power. So I want to use the strategy where we use logarithms to help us solve. Now, I already have my equation in the desired form. I have each exponential expression isolated on each side of the equation. Now we're going to apply a logarithm to both sides. It does seem very tempting to use either log base 4 or log base 3. However, those aren't necessarily calculator friendly. Instead, we're going to stick to common log or natural log. Here, I'm going to apply the natural log to both sides, just because natural log is 2 letters as opposed to log, which is 3. But this will work no matter which of the two you pick. Now that I have logs in my equation, I can use the logarithmic properties to help me rewrite the equation. Most specifically, the power rule. The 3x plus 2 is a power on the left-hand side. That comes out in front of the log as a coefficient. And the same thing goes on the right-hand side. The 5x plus 4 is a power. The logarithmic property lets me write that out as a coefficient. Despite the natural log of 3 and natural log of 4 in the problem, our equation is linear. Natural log of 3 and natural log of 4, they're both numbers. They're no different than the number 2 or 10. So now I want to solve this equation as if it's a linear equation. I'll start off by distributing in my values, my natural log of 4 on the left and my natural log of 3 on the right. And when I do, I have 3x natural log of 4 plus 2 natural log of 4 equals 5x natural log of 3 plus 4 plus natural log of 3. The next step in our strategy to solve linear equations is we want all of our x terms to one side, all of our non-x terms to the other. I'll move all my x terms to the left, so I'll subtract the 5x natural log of 3 from both sides. Now to get all my constants to the other, I'll subtract the 2 natural log of 4 from both sides. Now that I have all my x's on the left-hand side, x is a common factor of the two terms, and my goal is to solve for x, so I'm going to factor out the x. And we get x times the quantity 3 natural log of 4 minus 5 natural log of 3 on the left-hand side. Now to solve for x, keep in mind that 3 natural log of 4 minus 5 natural log of 3 is just a number. So I can divide both sides of the equation by that number. And when we do, we get x equals 4 times the natural log of 3 minus 2 times the natural log of 4, all over 3 natural log of 4 minus 5 natural log of 3. You could use logarithmic properties to simplify the numerator and denominator. However, you do run the risk of having to evaluate logs of very big numbers, which could be a problem with the calculator. If you chose to use common log instead of natural log, the only difference is instead of having ln in the answer like I do, you'll have log in your answer. And your answers may also appear to be different depending on how you move your terms around. If I decide to move all my x terms to the right and my constants to the left, you may instead get 2 natural log of 4 minus 4 natural log of 3 all over 5 natural log of 3 minus 3 natural log of 4. Both of these answers are the same. We can just obtain one from the other by multiplying top and bottom by -1. So keep in mind your answer can look different depending on how you approach solving this problem. In our next problem, we're going to try to solve 4 to the x plus 3 times 2 to the x minus 10 equals 0. The problem with this equation is the -10. This prevents us from isolating the exponential expressions on each side of our equation. Because of this issue, our strategy instead is going to be to try to make a substitution to see perhaps through this substitution we can make our equation into a different equation we do know how to solve easily. To help us see how to do our substitution, let's focus on the 4x. The reason why I'm focusing on the 4x is because we know 4 equals 2 squared. So 4 to the x would equal 2 squared to the x, which equals 2 to the 2x. Now the reason why this is helpful is I already have a 2 to the x in my equation. Now I can see my first and second term are some transformation of 2 to the x. So I'm wondering now if my substitution should be 2 to the x. To help me see that a little bit better, we're going to rewrite the 2 to the 2x in the first term as 2 to the x quantity squared, using the power to a power rule again, this time making the 2 the outer power. Now I see the 2 to the x's in the first and second term. So to solve, I want to make u equal 2 to the x. And with that substitution, we have u squared plus 3u minus 10 equals 0, which means our original equation was an equation in quadratic form, once when we substituted out the u to the 2x. Now we can factor our left-hand side to solve our new quadratic equation for u, and we get u plus 5 times u minus 2, which means u equals -5 or 2. But that's just the value of u. Remember, we were trying to solve for x, and u was 2 to the x. So from our work, 2 to the x is equal to -5, or 2 to the x equals 2. How do we solve 2 to the x equals -5? Well, think about the range of our exponential functions, b to the x. The range of exponential functions is the set of positive numbers. So it's impossible for an exponential function to be negative. So is it possible for 2 to the x to equal -5? No. So there's no solution from the first case. If we look at the second, 2 to the x equals 2. Well, 2 is the same as 2 to the first, so we can see x equals 1. So our only solution to the equation is x equals 1. Next, we're going to solve e to the 2x plus 2e to the x plus 1 equals 0. Unlike the last example, our two exponential expressions in the equation already have the same base. So this gives me the idea that perhaps our substitution would be u equals e to the x. To confirm this, I can rewrite e to the 2x as e to the x squared thanks to the power to a power rule. So I have e to the x squared plus 2e to the x plus 1 equals 0. Now we can make our substitution, and I have u squared plus 2u plus 1 equals 0. U squared plus 2u plus 1 is a perfect square trinomial, and factors to u plus 1 squared. Take the square root of both sides, which means u plus 1 would equal 0. No plus or minus because -0 and +0 are still 0. And then subtract 1 and we get u equals -1. But remember, that's only the value of u. We need to find the value of x. Our substitution was u equals e to the x. Since u equals -1, that means e to the x equals -1. But can e to the x ever be negative? No, it's impossible because the range of exponential functions is the set of all positive numbers. So e to the x can never be negative. So our equation has no solution. Keep in mind, in general, it is possible for exponential equations to have no solution. This is because exponential expressions can never be 0, nor can they ever be negative. So anytime I see b to the x equals something that is 0 or negative, that indicates we have no solution. Next, we're going to return to how to solve logarithmic equations. We discussed a little bit of how to solve logarithmic equations back when we first introduced logarithmic functions, but now that we have more properties, we're going to revisit strategies of how to solve them. First, we're going to solve log base 2 of x plus log base 2 of x minus 1 equals log base 2 of 3 plus 1. First, we're going to rewrite our logarithmic equation, so that way all logarithmic terms are on one side of the equation, and all constant terms are on the other. If we don't have constant terms, meaning all of our terms are logarithmic, there is a slightly alternate way we can go about solving. But if we look at the example we're trying to solve now, we do have a constant term, which is +1. Since the +1 is on the right, to get all of my logs on the left-hand side, I'm going to subtract log base 2 of 3 from both sides. The log base 2 of 3 will cancel on the right, and on the left, I'm going to begin to condense, which is step 2. For the log base 2 of x plus the log base 2 of x minus 1, since I'm adding them, to condense them, I multiply their inputs, but I'm subtracting by the log base 2 of 3, and to condense that, I would divide by that input, which is 3. And this will still equal 1. Now my equation is in the form of log base b of u equals m, where u is an expression and m is some number. Now I'm in a similar situation to what we saw back when we first introduced logarithms. To help us solve from here, we're going to rewrite our equation in its equivalent exponential form. And that'll give us 2 to the first equals x times x minus 1 over 3. Now that we're in exponential form, we can solve the resulting equation. We can do that by multiplying both sides by 3, and we get 6 equals x times x minus 1. We can distribute in the x, and we get 6 equals x squared minus x, and we can see our equation is quadratic. So to finish solving from here, we'll make one side 0 by subtracting 6, factor to x minus 3 times x plus 2, and set each factor equal to 0 and solve. We get x equals 3 and negative 2. Unlike exponential functions, logarithmic functions do have restrictions on what we can input into them. Exponential functions are undefined if I try to evaluate a logarithm at a negative value or 0. This means we must check to make sure we didn't get any extraneous solutions. First, we're going to check x equals 3, which means when we plug in 3, we have log base 2 of 3 plus log base 2 of 3 minus 1 equals log base 2 of 3 plus 1. Simplify what's inside of our logs, and so far, I have log base 2 of 3 plus log base 2 of 2 equals log base 2 of 3 plus 1. So currently, I'm not trying to evaluate a log at a negative value, but to continue checking to make sure I'm right, we know log base 2 of 2 equals 1. And we see that both sides simplify to log base 2 of 3 plus 1, meaning x equals 3 is a solution. So let's write that down at the top. Next, we're going to check x equals negative 2, the exact same way we checked x equals negative 3. And when we do, we have log base 2 of negative 2 plus log base 2 of negative 2 minus 1 equals log base 2 of 3 plus 1. If we take a look, we are trying to evaluate the log of a negative number. So that would be undefined, which means negative 2 is an extraneous solution. So our only solution to the equation is x equals 3. One thing to note, we can get negative solutions to logarithmic equations. Negative values for our variable are perfectly fine as long as they don't make inputs to the log negative when we plug them back in. Next, we're going to solve the natural log of x plus 3 plus the natural log of x minus 3 equals 2 times the natural log of x minus 2. Unlike the previous equation, we don't have a constant term. Since we don't have a constant term, what we can do instead is we can condense the logs on each side of the equation into a single log and then use the one-to-one property of logarithms. That is, if we have log base b of m equal log base b of n, then m must equal n. So if I take a look at this equation here, on the left-hand side, since I'm adding two logs together, I can rewrite that as the natural log of x plus 3 times x minus 3. As for the other log, because I have the coefficient of 2, I can use the power rule to make it into an exponent inside of the log. And I can rewrite the right-hand side as the natural log of x minus 2 quantity squared. Since I now have the natural log of one input equals the natural log of another, according to the one-to-one property, the two inputs must be equal. That is to say, x plus 3 times x minus 3 equals x minus 2 squared. Now our equation is beginning to look quadratic, so let's expand. The left-hand side after foiling will be x squared minus 9. The right-hand side, if we write as x minus 2 times x minus 2 in FOIL, or if we use our special multiplication rules, becomes x squared minus 4x plus 4. Next, if I subtract x squared and add 9 to both sides, we can see one side will be 0, but x squared minus x squared, they'll cancel, leaving us with negative 4x plus 13, which means our equation is now linear. And if we solve by subtracting 13 and dividing by negative 4, we get x equals 13 over 4. Even though we have one solution, we still need to check to make sure none of the inputs of the natural logs will be negative when 13 over 4 is plugged in. Now remember, when we do check, always check into your original equation. Now we simplify what's inside of our logs. 13 over 4 plus 3 will be 25 over 4. 13 over 4 minus 3 is 1 over 4. 13 over 4 minus 2 is 5 over 4. So I'm not trying to take the natural log of 0 or a negative number. So far it looks like everything's going to be defined. Since I know everything is going to be defined, I can continue checking to make sure my answer is correct. And I could either throw this into the calculator, or I can continue using logarithmic properties since I know everything is going to be defined. Using the logarithmic properties, when I add my two logs on the left-hand side together, I know I'm multiplying their inputs. 25 fourths times 1/4 is 25 sixteenths. 2 times the natural log of 5, bringing that in as an exponent. The right-hand side will become the natural log of 5 fourths squared. 5 fourths squared is 25 over 16. So I have the natural log of 25 over 16 equal natural log of 25 over 16. That is true. Everything is defined. So x equals 13 over 4 is our solution. Before you go and use the logarithmic properties to finish checking, make sure you do check to make sure you're not taking the natural log of any negative numbers or 0. If you don't check and you just go ahead and use the logarithmic properties, you are going to miss that detail. So always check to make sure your logs are defined first before using any properties.